Okay, good morning. This is our last lecture before our first exam. And in this class, we will be talking about reliability. So previously, we discussed the idea or notion of validity, right? The reason that we care about validity is because um, s- social science and science in general relies on observations. And because many phenomena that scientists are interested in cannot be directly observed, right? It can be natural selection, it can be some um, interesting physical phenomena um, where we cannot directly sense it by our eyes or our other sensory organs. So we'll have to rely on some kind of scale instruments to index to capture um, what we're interested in. And the problem is, whenever you're using a scale or instrument in general to measure something, there's always a risk of not measuring what you intend to measure. So, and that's where the concern for validity comes in, right? Validity here means the validity of the instrument. And we'll say that our instrument is valid when it measures what we intend to measure, and it's not valid when it does not measure what we intend to measure. So, how do we know? At least there are three criteria for judgment, to judge whether or not or to extend a scale or measure is valid. So we have face validity, we have content validity, and we have predictive validity, right? So face validity simply means, we judge the validity of a measure or a scale by its face value. So if you want to, for example, measure a person's aggressiveness, you would just ask, how aggressive this person is. So that's a face valid scale because, well, it makes sense to directly ask people about their aggressiveness. But we also talk about the risk of simply relying on a face valid measure because in many times a concept or a variable is multidimensional. That means you have more than one indicators for the variable. So for example, for aggression, right, we have physical aggression, we have verbal aggression, we have indirect aggression. So then these three aspects of aggression cannot be captured by a one item question on how aggressive a person is, right? Because people might interpret, this question different ways, and this will lead to biased observations. So once you have a scale that can capture or cover all three aspects of the interested variable, then we say that your measure is content valid. Lastly, we talk about this idea of predictive validity. That means whether or not you can use the measure that you try to validate to predict the measure variable that by theory should relate to the variable that you're trying to measure. Right? That sounds like a mouthful, but okay, so that will be a sort of a waste of time if I recapture the whole idea of predictability here. So if you still have questions about this type of validity, just go back to the video clip of our previous lecture or ask me face to face in tomorrow's uh, Q&A session. Okay, so let's continue. We said that validity is only one criterion of the quality of measurement, right? So when we ask ourselves, how good our measurements are, we can evaluate our measurement, you know, um, by two criteria. First one is validity, and the second one is reliability. So what does reliability mean? We say that a measure is reliable if it provides or yields the same result or highly similar results time and time again, right? So that means, invariance, right? Variance means change, but invariance means, it doesn't change. So invariance is a signature of a scale being reliable. In other words, for reliability, or for the idea that a measure is reliable, is that this measure is consistent. That means, it provides highly similar results across time, across situations, across people. Or you can repeat, right? You can repeat the result across time, across situations, across people. So repeatability will also be a different term, expressing the same idea as reliable or reliability does. So again, we use this target metaphor, right, to illustrate the idea of reliability. So again, we treat, a variable as a target, or treat this target as a variable. So again, if we throw a dart and this dart hit on some part of this variable, we're saying that we're trying to measure this variable, right? So we hit the center of the target. That means, we have a pretty good, precise measure or measurement of our variable. So precision, right? Precision will be another word for validity, right? That means we're totally on target. But reliability has a very different meaning. So it is possible that you throw, let's say, 3 darts. You're not totally confident by throwing 1 dart, or not totally confident by just measuring your target variable only once. So you try to measure it multiple times to see if you get similar findings or similar observations. Unfortunately, in this case, the 3 darts land on totally different parts of this target. That means you don't have good reliability here, or it means your measurement, your scale is not reliable. So in another situation, in this scenario, right, you throw 3 darts, or you measure the same variable 3 times, and this time the 3 darts land on very closely to each other, right, on the same area, and very, very close to each other. And when this happens, we say that your measure of the target variable is very reliable, because it provides very consistent observations, or scores, or values, or observations. Okay? So in other words, for a measure to be reliable, you don't have to, well, for a measure to be reliable, the measure does not have to measure what you intend to measure, right? So if, for example, right, we have a measure that it is very accurate, or very precise, and very reliable, we should observe this situation. That is, back to the throwing dart metaphor, right? So the 3 darts should, first of all hit the center, or land in an area that's very, very close to the center of the target. So in this case, your measurement activities are very reliable, and at the same time very valid. In this situation, right, you do have very reliable measurements, because the 3 measurements you have yield very similar findings or observations, because on this dart, in this dart metaphor, 3 darts, the land in in a very nearby situation or area, right? But at the same time, they're not valid because they're very far away from the center of the target. That means despite being reliable, these three measures are totally off target. They're not valid at all. Okay? So here, there's a sort of philosophical connection or relationship between reliability and validity, right? So first of all, you can have very reliability. You can have very reliable measures or scales, but reliability does not necessarily lead to validity, right? Validity, as in this case. Very reliable measures, but they're not valid at all, right? They can be totally off. They can be reliably wrong, right? But the reverse or the converse is not true because validity must it must imply reliability. That is, if a scale is precise, is accurate, it must be reliable. Why that's the case? Well, I'll let you think about it and we'll return to this question later. Okay? But for now, just understand the definition of reliability. But keep this question in mind. Why a measure being valid, it must also be at the same time reliable. Okay? We'll return to this question later. Okay, so now we have a question after defining reliability. That is, how do we quantify reliability, right? In other words, what are some criteria of judging whether a scale is reliable or not? To understand this, question, to address this question, we must understand a theory, a very influential theory about reliability. Okay, so here we're not talking about any communication theories. There are no, uncertainty reduction. There are no social identity, but it is a theory of method. It is called the true score theory. The true score theory actually is a very simple idea, I should say. It simply says any measurement, any observation, in other words, right? Another word for measurement will be observation. Any observation or measurement will be the sum, right? Additive components, composite, right? Additive composite. That simply means, sum, right? It's the sum of two factors. The true score of a variable and error. So in the formula form, we have a measurement or an observation, right? X. It is the observed value. That is, you imagine you're measuring your own weight. So you stand on a weighting scale and you look at the screen and obtain a reading of it. You say, well, 65 pounds. So this 65 pounds, based on the reading, will be your observation, will be the observed value of your weight. Because that's what you see. That's what the scale tells you. But it turns out, according to this true score theory, you can sort of dissect or break this 65 pounds, or you can break this observed value in a more general sense, right, into two components. The first component is the true value of your weight or your true weight and error. Okay. Now we'll talk about what we mean by a true value and error in a minute, but for now, just keep this in mind. That is, in almost all measurement activities, We can only obtain observations. And true value is very, very likely unknown, right? Here I use quote unquote God. Simply means, it's not known by us, right? Unless you have some supernatural ability, right? You don't have to be any kind of God, whatever God you believe in, right? I do not mean that. I do not mean, for example, Buddha would know the true value. Um, this simply means, we as human beings do not have knowledge. You actually do not know your true weight. That's simply what it means. But you ask, well, wait a minute. How can I not know my true weight? I stand on a scale, and the scale tells me I weigh 65 pounds. Isn't that my true weight? Well, this theory says this is not your true weight. This is only what you observe according to the scale. Your true weight might be 65 pounds. It could be. By chance, your true weight is exactly what you observed. But more likely, but chances are, your true weight, if the scale is operating normally, is functioning properly, your true weight will be slightly off what you observe, because you will always obtain a certain amount of error when you rely on some kind of instrument to gain knowledge about something. So this is what we mean by saying that, you know, almost all knowledge that we gain by observation, right? Whether or not we're talking about knowing the physical world, right? Knowing, cells, knowing particles, knowing substance, whatever, right? Or to know about our social world, to know about what other people are thinking, what other people is doing, to understand the emotional feelings, whatever, right? So whatever knowledge that you're trying to gain through observation, that knowledge in 99.999% of the time is only approximate. That is, it is not true, right? It is only in a state that is very close to the truth, but it never is the truth. So, in other words, as we just said, it will never be able to uncover the complete truth. But what you can do is to get closer and closer to the truth. And of course, how far away you are from the truth, that is, the discrepancy between your observation and the true value, if anyone knows about that at all, will depend on how precise your measurement instrument is. Right? That will be another way of saying it depends on how much error your instrument will make. So let's look at an example to understand this idea. So let's say it is written in a book by the university from the provost that each lecture given on Tuesdays and Thursdays by the Kanji department should be or must be 75 minutes long. Now my question for you is this. Is this 75 minutes, is this value, right? This is value. And this is variable, right? The length of each class session, right? That's variable, and now we have a value. So my question is this value 75 an observed value, a true value, or an error? I'll give you 2 seconds to think about it. Okay? Time is up. Answer is this 75, this value for the variable length of a class session, it is a true value. It is not an observation because when the provost is making this law, this regulation, this rule, he or she does not really go to a class and actually time it. The person, the provost, with his or her assistants, most likely thought that 75 is a good amount of time for a certain amount of knowledge to be introduced, to be discussed in class. And that's why they say, aha, let's make this a rule. Let's make this an expectation. We expect, in other words, the provost expects, the professors accepting this rule also expects that in theory, right, each class should be this much long, right? So that's why we say that the 75 minutes is a theoretical value. In theory, it should be this much long. It is also an expected value, right? That means, we think that each session ought to be this much long. It is something that we expect. So whenever you see terms, words like should be, ought to be, right, must be, have to be, most likely we're talking about, in the language of true score theory, right? We're talking about true values. That is something we expect, right? But you say, well, hang on a minute, Andrew. You just said that, true value is something that only gods will know, right? Well, that's true, right? And this idea does not contradict this question here about the 75 minutes. When I say that only a god can know the true value, I mean, that is, from the perspective of an observer, right? And, an observer, if, the observer is human being, right? Without any supernatural ability, right? Will never be able to very precisely measure how long, for in this case, right, the class really is, right? In contrast, the god here, quote unquote, will be the provost, because he or she only stipulates that it should be this much long. But even he or she, the provost, when this person comes to a classroom and actually delivers a lecture by him or herself, he will also not be able to know whether or not after a certain period of time it is 75 minutes or only 74 minutes. His or her knowledge about the length of the classroom when this person starts to observe the length of the classroom will also become approximate. But any one of us, not just the provost, you, me, or other people in this school, they can similarly stipulate. They can set up a rule and says, well, the class should be this much long. But in actuality, whether a professor or student actually stand or sit in a class for exactly 75 minutes, not a 1 second more, not a 1 second less, and that will be a mission impossible, right? So we're not, contradicting ourselves here, okay? So here, leads to, our question, right? The core question is, given this stipulation, given this rule, how do we know whether or not or how successfully we conform to this rule, conform to this stipulation, whether or not we meet the expectation of our provost, right? That is, how do we exactly know that, we have, spent exactly 75 minutes, not a 1 second more, not a 1 second less in a classroom, okay? So here comes our first example illustrating the idea of true score theory. That is, how much time has elapsed. if you ask this question to a person living in ancient times, if you're lucky, that is, if you asked a person from a civilized culture, they will look at this, radius, sun diagram, and tell you, we've probably spent 2 or 3 degrees. Well, I'm just imagining what they will say, right? We'll probably spend about a certain degree of time here. Because when you measure time by sun diagram, your measurement will be in degrees, right? In how much degree has this needle, or the shadow of this needle, has moved from its original point, right? 3 degrees, 2 degrees, I don't know. They don't know. They can only say with a certain level of confidence. Okay, now time, flows, and you've asked this question to someone living in the industrial age. Now you will get a more precise answer. This person will be able to tell you, well, maybe, right, we've spent 2 minutes together. But then, because this clock only has two hands, it doesn't have a second hand, right, the hand for seconds, you will never be able to know how many seconds has elapsed. You can only roughly know that, the time in terms of minutes. But then nowadays, right, if you use a digital clock, you not only have very precise measures of hours, minutes, but also you can relatively more precisely know about seconds. So here I say, well, it's, 5 hours, it's, 5 p.m., 52 past 5, not just that, but 52 minutes and 3 seconds past 5 in the afternoon, right? How precise that will be. But you think that is the most precise measurement of time? You will be wrong, because, with iPhone, you not only have seconds, you have milliseconds here. 3 seconds is 3.58 seconds, right? Here is just only 3 seconds. But now we have 3.58 seconds. These are milliseconds, even more precise. Okay? It's minutes, seconds, and milliseconds. So as you see, maybe in another 10 years, we'll have more and more precise measures of time. That means our knowledge, right? Our knowledge about time, we use time as, the target of knowledge. So that means our knowledge of time here really depends on the kind of instrument that we're using. And regardless what instrument we're using here, a sun diagram, a industrial age clock, a digital clock, or iPhone clock, whatever tool we use, there always will be a part of the objects we would like to know, but we couldn't know about, right? That simply means, there's always a part of the knowledge that would not be able to obtain because of the limitation, because our, sensory systems is limited by the degree of precision of tools. Okay? And that part of knowledge that we'll never be able to obtain, right? Or in simpler terms, anything that's not observable, anything that's not measured, we call an error. So error here, in the context of true score theory, does not mean a mistake. It could be a mistake. A mistake will be a source of errors, but errors are not necessarily mistakes, because it is something, here is definition, right? It is something that is not measurable. That's something beyond our ability. Okay? Our second example will be this. Let's say Andrew take an exam. The exam is designed to be of 100 points, and Andrew scored 85 points out of 100. So let me ask you, what is this 85? Is this score a true score? Is this score an observed score? Or is 85 an error? I give you 2 seconds to think about it. 1 and 2. Answer is 85 is an observed score because that is what the teacher told Andrew. Right? Chances are the teacher wrote 85 on the exam paper of Andrew, and therefore Andrew is capable of knowing that, okay, I got an 85 this time. So now we imagine that we now play God, and through a certain means, we know that the true math skill or aptitude of Andrew is 89 out of this 100 points. Okay? Now my question is, now that we have the observed score, and now we have, well, this is the observed score, right? And now we have the theoretical value, expected value, or the true score of Andrew's math aptitude. My answer is, what is the error? How much is the error? I give you 2 seconds to think about it. Error, in this case, after 2 seconds, speculation, is -4. Because it is -4 because we know that the formula for true score theory is the observed score equals true score plus error. Now we have true score as 89, observed the score as 85. Now we solve for E, right? Error. How do we do that? Right? We put E on this side of the equation and then use T to minus X. That is 89 minus 85. That gives you 4. And then we move this negative sign from here to here, right? From here to here, it will be -4. So, right, error will be -4, right? Another way to think about it is this, right? We put error, they'll put the, negative sign ahead of, in front of 89, and this will become positive sign, and then that will give us -4, right? Another way to think about it is, we still work, on this formula, and we just can guess, right? So what kind of value when added to 89 will give you 85? It must be -4, right? So 89 plus -4, that essentially equals to 89 minus 4. 89 minus 4, that's 85. Okay? So that's our error, -4. So when we have a negative error, we'll say that our observation here is negatively biased. It's negatively biased from the true score here, right? So if we have negative biases, you might ask, well, do we have positive biases? That is, can we possibly have positive errors? Can we? Think about it. Give you 2 seconds while I drink some water. Okay, the answer is, of course we can. And we can think of a scenario that will give us a positive error. So imagine this time Andrew's true math aptitude is 81 out of 100. And he scored 85 on an exam. Okay, so what is the error? 4, because we have x equals to, long leg here, x equals to t plus error, right? So if x here is 85, true score is 81, what must be e so that when you add e to t will give you 85? Well, it must be 4, right? So 81 plus 4, that's 85. Okay, so error in this case is 4. So in this case, we're saying that it means, right, the error this time positively biased the measure. Right? So bias, as you see, is not necessarily a bad thing, because bias can mean the error decrease results in a smaller observed value relative to the true value. You could also mean that, this error increased the observed score relative to the true value. Okay, so it's really a neutral term here. Okay, so it turns out that not all errors are created equal. There are different types of them. So there are 2 types that we'll talk about. We have random errors and we have systematic errors. So systematic errors simply is any error that systematically affects the measurement of a variable across a sample of objects. Right? Imagine you administered a questionnaire to 50 people. Right? So a systematic error would occur when the score of all 50 people when filling out your survey, which will be the same across, the surveys, well, all 50 people, finished the same survey, right? A systematic error would occur once the scores of all 50 people will be similarly affected. And by being similarly affected will mean, right, the following. So imagine this time you're not taking a survey, but you're taking an examination. And then it turns out that you take this examination in a very noisy environment. Imagine we, again, play God, right? So that we know the true value or the true average score for this class of people will be 80 points, right? But because of the noise, because of the noisy environment in which the exam took place, everybody scored 10 points less than their true score. Well, if everybody scored 10 points less, that means the average will be 10 points less, right? Because, well, that's exactly what the sentence means. So this 10 point, will be an error, right? Because the observed average score will now be 70 because everybody scored 10 points less. So on an average, the score will be 10 points less than the true average, right? So now the 10 point will be a systematic error. It is systematic error because, first of all, as this example illustrates, everybody is affected, right? It's not that only half or 2/3 of the sample are affected. Instead, everybody was affected. Second, everybody is being affected by the same amount, right? Because here we said everybody scored 10 points less. It's not that Andrew scored 5 points less, whereas Angie scored, 6 points less. That would not be a systematic error if that happens, right? And lastly, right, everybody is being affected in the same direction. It's not like that. It's not like Andrew scored 10 points less, whereas Angie scored 10 points more, right? 10 points less and 10 points more, they have the same amount, 10, but the direction are opposite to each other. Okay? So this will be our definition of a systematic error. Everybody is affected by the same amount in the same direction. So graphically, we can also represent this idea of a systematic error. So a systematic error can be illustrated, can be graphically represented as follows. Imagine this is a distribution, right, without any systematic error, so that the average here will be the true average, right, without any error, without any systematic error. We're also not considering random error in this case, right? So this distribution simply means, right, there are many people who scored 80. There are many people whose true score is 80. There are a few people whose score are, well above 80, and there are a few people whose true scores are well below 80, right? Lots of people in the middle. Now, if we add systematic error to this distribution, what's changing and what is only changing will be the average score, because everybody, right, is affected to the same extent. You can imagine that we have a person here, right? So person here, we can sort of find out its, true, true score is 70, while the true average is 80, right? Now, if a systematic error occurs, right, in this case, everybody scores 10 points less, then this person will be here. About here, I would say. In this case, this person scores about 60 points, right? But then, if everybody is 10 points less, what is only changing then is the average, right? Nothing else is being changed, because no one is going to score higher, and no one will be scoring lower by a larger amount. Okay, if some people are scoring lower by a larger amount, then this tail will be even wider, because now we have some people that scores perhaps lower by 40 points. And if at the same time there are some other people who scored not lower but higher because of the error, this tail, right, this tail will also be longer, because now someone is scoring actually very high, much higher than the average. Okay? But now, because we said that only systematic error occurs, that means everybody is affected, everybody is affected in the same direction by the same amount. And therefore, the shape of the distribution will not change. What's only changing is the average. Okay? So the conclusion is, right, if a sample of scores only has systematic errors, then the only thing that will change will be the averages. Okay, so now we have a second type of error, and we call them random errors. Random errors, as the term itself implies, are errors that randomly affect a sample of scores, such that not everybody will be influenced. It could be the case everybody is influenced, but it doesn't have to be. The second feature is they're not influenced by the same amounts. In our example, of taking exams, right? Some people might score lower by 10 points, some people might score lower by 5 points. They're not influenced to the same extent. And lastly, the direction of the influence might be different across people, right? Some people have a higher score, some people have a lower score. Okay? So, for example, right, exam was being administered at noon in the summer, in a very warm summer. Again, we imagine that we play God, sorry, and we know that the true average score is 80. Okay? But this time, instead of everybody being influenced to the same extent by the same amount, some people like me cannot simply keep awake in a warm summer noon, right? I'll fall asleep. Whereas others are very comfortable with this time. And some other people, also like me, will be thinking about traveling with friends and family instead of thinking about taking exams. Okay? So in other words, there are many in this time different factors that affect the sample of students' performance on the examination. So some will score higher when they're very focused instead of not motivated, when they're very comfortable with, staying awake in the afternoon. So these people will score much higher compared to people who cannot stay awake in the afternoon, compared to people who are not motivated, compared to people who, for various other reasons, right, do not perform well. So in this case, we have, again, a distribution without any type of error. In this case, without any random error. So again, we have a true average score here that's 80. But we can imagine that, right? So in this case, some people will be negatively affected this time. So the tail, right, instead of here, will be wider. Whereas other people, they like taking exams in summer and in the afternoon, therefore they score much higher due to this random factor, right? Taking exam on 1 p.m. in the afternoon, that's a random factor. So this time you will say, and you will see, when the sample is large, meaning there are enough people who score lower because of taking exam at that hour in the summer, and because there are also a very large or equal amount of people who would take exam in 1 p.m. in the afternoon and be very comfortable about it. Therefore, they score higher relative to the true average. So these two group of people scoring higher and scoring lower, they will cancel each other out on the effect to the average. That means what's changing this time then will be the shape of the distribution. Some people score much lower, Well, some people score lower, some people score much lower, right? So we have, a little bit of a discrepancy here, and then we have a larger discrepancy here. That means some people are scoring lower, but only by a little bit, whereas other people are scoring much lower, right? A lot more lower than these guys. At the same time, some people are scoring a little bit higher, whereas other people are scoring much higher, right? But because imagine we have a very large sample size, that means just by chance we'll have equal amount of people who score lower and higher in different directions. We'll have people scoring lower, and people who score higher by the same amount. We'll have people who score lower, and we'll have people who score higher by the same amount. And therefore, despite the fact that the shape of the distribution now is changing, becomes much wider, right? The average stays the same, because these guys, the effect of these guys on the average is cancelled out by these guys. The effect of these guys on the average are cancelled out by these guys. The effect of these guys on average are cancelled out by these guys. And that's why the average would remain the same. Okay? So this wider distribution then will be the distribution with random error. But if only random error is present, right? Only the spread, right? This distribution is spread it out much more than the original one, right? Later on we'll see and we'll learn that spread essentially means variance. There will be more variances, more differences across this group of people. But the mean will remain the same, because the effect on the means, potential effects on the means, in other words, the individual errors, right, are cancelled out because the errors are in different directions. Okay? So then we can rewrite the error like this. We have total error, and we now know that under total error we have systematic error and we have random error. Okay? So in other words, the total error can be decomposed into two parts. So now the question is, it seems that errors are inevitable, and rightfully so, right? You either have something that's systematically influencing your observation, or you have something that's random. Something randomly affects your observation. Either way, you will have some errors there involved in your observation. So the question is, if errors are inevitable, are bound to happen, which error do you prefer? I'll give you 2 seconds to think about it. If errors can be decomposed into systematic errors and random errors, and if errors, whichever type it is, are inevitable, bound to happen, then which error you would rather happen instead of the other? The answer is we'll rather have systematic errors if errors are inevitable, because we know that systematic errors happen to everyone. They change everyone's score in the same direction by the same amount. That means we can correct for it. Right? That means we can remedy the situation by doing some simple calculations. Or we can adjust, right? Adjust the error so that we still have pretty good knowledge about the true values. Okay? Alright, so now we know why we have this concern for reliability. Because every time we measure something, we introduce a little bit of error to our measurement, right? And because of this small amount of error, sometimes can be big, our measurements would not be the same every time, right? Because the error is different, right? We can sort of understand this idea by, again, writing out this formula, right? We want, so a totally reliable measure will be, that is, if we repeat the observation multiple times, right? Let's say we measure a variable for the first time, we'll have some kind of error. For the second time, we'll also have some kind of error, right? For the third time, we have some other type or amount of errors. So each time, because we're measuring the same variable, the true score remains the same. Now, if, let's say, our measures are totally reliable, then that means either we don't have any errors, that is, all the errors will be 0, right? Or all the errors are the same, right? That will give you or give us identical observations. But that's rarely the case, right? Errors are very unpredictable. They're random stuff, right? Even though we have systematic components to errors, but random errors are never avoidable. So that means each time we'll have a slightly different error, and that will result in some slightly different observations, slightly different observational scores. And that will result in we yielding or producing inconsistency or inconsistent scores. Okay? And that's why we have to be concerned with the reliability of our measures. Okay? So that's the theoretical reason why reliability is concerned. Okay, so now we have grasped a general understanding of reliability. Let's talk about specific types of reliabilities. We have test-retest reliability. We have split-half reliability. We have Cronbach's alpha reliability. And these two collectively are known as inter-item reliability. And lastly, we have inter-rater reliability, right? And now we'll go through them one by one. Don't worry, they're very simple ideas. Now you understand what reliability is, right? This will come very fast and very straightforward. So test-retest reliability, for example, if we have a 4-item scale for extroversion, that is, we use these questions, to measure how extroverted you are. So I give you one example item. I feel comfortable around people, so this is an item, right? Imagine we have 3 other similar questions. So to establish that these items or this 4-item scale is reliable, right? One way to do that will be to give the full scale, right? All 4 items to the same group of people at different times. For example, I can administer this 4-item scale tomorrow and administer the same scale to the same group of people a week later. So we have 2 time points, time 1 and time 2. And what we can do then is to see how well or how strongly the scores at time 1 correlate with the scores from the scale at time 2. If the scores from time 1 highly correlates with the scores at time 2, then we have high test-retest reliability. That means, the scale, the 4-item scale, yields consistent results, right? Yields consistent results across time. So that's evidence for test-retest reliability. Okay, very simple. But a problem with, this way of establishing reliability, as you can imagine, will be memory. That is, the high correlation between time 1 and time 2 could be artificially produced by people memorizing the answers to the questions. Because, after all, you administer the same questionnaire to people and to the same group of people, right? People, when answering the questions at time 2, will think, well, didn't I just answer this question a week ago? I remember I scored a 5 on this question, and I will score a 5 again on this question, on the same question, right? So that will give you very consistent scores, but this consistency is not due to, is not, probably not due to your scales being good, but simply due to people memorizing the scales. So that could be a big problem. To solve this problem, right? Okay, so here's the reason, right? The problem. To solve this memorizing problem, we only administer the scale only once, right? So that totally avoids the problem of memorization. But a problem though is if we only administer the scale once, that means we only have one score. We only have one average score from these, 50 people or 30 people. Doesn't matter, right? We only have one score. And we know that for correlation to happen, we at least need two scores. Because if we only have one score, there's nothing else for it to correlate with. And the correlation of a variable to itself will always be 1. And that doesn't help at all, right? So that means we need a second score for us to perform some kind of correlation here to establish that, these items, this scale, are reliable. So the solution is we do administer the full scale to a group of participants only once. But when we analyze the scores, we randomly split the scale into two halves. Remember, we have 4 items, right? Remember that we have 4 items. So we gave all 4 items to participants. But when analyze their scores, we randomly pick or randomly divide the scale into half. So for example, we can sort of divide it conveniently here, right? So we treat the average of item 1 and 2 as 1 score, and we treat the average of item 3 and 4 as 1 score. So these 2 items will provide a score, and these 2 items will provide a second score. Now we have 2 scores, and now we can see whether these two scores, whether these two scores correlate with each other, right? If they do, that means these items are very similar. They yield very consistent scores. Okay, so this is the idea, right? We see how strongly the scores from the first half correlate with the scores from the second half when the two halves are randomly created. So we call this split half reliability. Okay. So again, if we have a strong correlation between the score from the first half of the scale and the score, from the second half of the scale, we have high split half reliability. So for example, right, we have this extroversion scale that has 4 items, 1, 2, 3, 4. We give all 4 items to a group of participants, but when we collect their survey responses and analyze their scores, we say, well, let's randomly sort the 4 items into 2 halves, each half containing 2 items. Okay, so by random, we say, well, item 1 and item 3 were randomly chosen to form the first half, and item 2 and item 4 randomly chosen to form the second half. So each half produce one score, right? By averaging the two items. Averaging item 1 and 3 give you one score. Averaging the score of from item 2 and 4 give you a second score, and then compute the correlation to see whether or not you have good correlation. If you have good correlations, that means, these items, right, despite being randomly split into halves, provide or generate consistent scores. But here's a problem with the split half reliability, and that is the between half correlations could vary. And why is that? It's very straightforward to see, because we have four items. How many ways, let me ask you, are there to create two halves from these four items? You could say, well, let me take item 1 and 2 and item 3 and 4 as the two halves. But that's not the only way of creating two halves. We can also use 1 and 3 as the first half and 2 and 4 as the second half. We can also use, where's my mouse? We can also use item 1 and item 4 as the first half, and therefore 2 and 3 as the second half. Okay, so there are multiple ways, in other words, to create the halves. But each time we can only create one combination, right? We either have 1 and 2, or we have 1 and 3, or we have 1 and 4. And by picking different halves, we produce different correlations. And that's what we mean by, very likely, the between half correlations would vary, would not be the same, right? So the solution is we exhaust all the possibilities, we obtain all possible split half correlations, and we compute average. And we use that average as the index of how reliable our measurements is. Okay, so more concretely, right, we have four items. So what are the possible split halves? We have one possibility, a second possibility, a third possibility. And we denote them as alpha 1, alpha 2, alpha 3, and they're the correlation between. So alpha 1 will be the correlation between these two halves. Alpha 2 will be the correlation between these two halves. Alpha 3 will be the correlation between these two halves. Okay? And we see that because the halves are not the same. 1 and 2 definitely will be different from 1 and 3, and very likely will be different from 1 and 4. And because these halves are not the same, the correlations alpha 1, 2, and 3 will also not the same. Will also be very unlikely, right, the same. So after we exhaust all the possible halves and all the possible split half reliabilities, now what we can do is we take the mean score of the three, split half reliabilities, and this mean score will be Cronbach's alpha. Okay, very easy, right? Very straightforward idea. Now, lastly, we have. Oh, okay. So we said that Cronbach's alpha and split half reliability collectively they're known as inter-item reliability, right? Inter-item reliability is concerned with the idea that whether multiple items from the same scale produce similar measures. Well, they should, because they're from the same scale, right? All items are from the same scale, and presumably they're measuring the same variable. Okay, so as a rule, right, if we have strong correlations between the two halves, for example, right, then we have good inter-item reliability. So in addition to inter-item reliability, we also have inter-rater reliability. And inter-rater reliability concerns how reliable a group of observers are. You imagine, you being the judge of a beauty competition. And your job is to determine how attractive Andrew is. And when you do that, it is very intuitive that you should use multiple judges. Because, if you only use one judge, this judge could be very biased, right? So, in order to have a trustworthy, trustable result, you should use multiple judge. But the problem is, when you use multiple judges, the judges could still disagree with each other, right? For example, if on a 7-point scale, right, Judge A rates Andrew, give Andrew a 1, Judge B gave Andrew a 4, and Judge C gave Andrew a 7. They disagree with each other, and when that happens, we say that they have low inter-rater reliability. But imagine that all three judges gave Andrew very low scores. So this time, they will have high inter-rater reliability. They agree with each other. There is a consensus. Okay? So that's what it means. Alright, so that will conclude our lecture on the 4 different types of measures. Different types of reliability. Excuse me. Okay, so now lastly, let's return to our question. That is, can we have high reliability below validity? Can we have, at the same time, high validity below reliability? We said that at the upfront start of the class that this is possible. All right, let me change back to my red color. This is possible because, we can have a dart, right? A dart, a dart, a dart. A target. So we can throw 3 darts, all 3 of them being very far away from the center. That means they have low validity, right? Very far. So they have low validity, but they are clustered very close to each other. That means they yield very similar scores, and therefore they have high reliability. So that means this is possible. But it is impossible to have high validity below reliability, and this is pretty straightforward. Again, we have a target. Okay? In order to have high validity, we must have all the darts to land very closely to each other and at the center area of the target. And when that happens, we necessarily have high reliability. Conversely, if we have low reliability, that means the darts will be on different areas of the target. And when this happens, there's no validity at all, right? Because how do we know that, when these darts are land so far away from each other, how do we know that this one is measuring something we intend to measure while this one is not? Or this one is measuring something we intend to measure whereas this one is not? There's no way to tell. Okay? So high validity must imply high reliability, conceptually speaking. Right? So that will be the answer to our question. And here it is, our answer. High validity implies high reliability. Okay, so that concludes our lecture. And maybe I have one more sentence here, right? High reliability does not necessarily lead to high validity. And here's this scenario, right? High reliability, but low validity here. Okay, all right, so that will be the end of our lecture on reliability. So tomorrow we would have a Q&A session, and on Friday we'll have our first exam. So welcome to ask me questions in the Q&A session. I will send out another reminder to you later, and if you cannot make it to the Q&A session, welcome to drop by my office and we can talk face to face, or you can send me emails. Okay? All right, good luck, and I'll see you soon.